Hey Precalc, this is Blick, and I am going to work through a few of the problems here on 6.8 to help you as you work through them on your own. So, to use this video to its maximum potential, I would say follow along with me on your own copy of 6.8 as I'm working through them. I will do most of the problems, but not all of the problems. So for example, here on number 1, I'll probably do A and leave B and C for you. For number 2, I'll do some of these values. Maybe I'll just do like cosine and maybe tangent as well, and I'll leave the rest to you, etc., etc. So it might be a bit of a long video because I'll be going all the way through the entire handout. So feel free to scroll through if you need to get to a specific problem. It'll be later in the video. All right, so here we go. Number 1, we are seeing here that the intersection, the unit circle, and the terminal side of an angle, theta, in standard position, happens at the point P. The coordinate is x, p, y, p. Now, to visualize that, I'll zoom in a little bit here. That unit circle is a unit away from the origin. And so any point on here, xp, yp, is going to be exactly one unit away from the origin. So right here we would have that point xp, yp. It's 1 unit away. That tells us that the cosine value of this angle theta is going to be the adjacent side over the hypotenuse, which would be xp divided by 1. And so the cosine value here is going to be just xp. xp divided by 1 is xp. And the same is going to be true for the sine value as well. That 1 is going to be yp divided by 1, or just yp. Same is going to be true for tangent. It's going to be our opposite over our adjacent. So in this case, that is going to be yp divided by xp. That's going to be true for any point on the unit circle. So if that angle was 0, the cosine value would be the x value for that angle 0. And that point on the unit circle at 0 degrees, is going to be the point, is going to be 0, or rather 1, 0. 1, 0. So our cosine value will be 1. At 90, that'll be rotated up 90 degrees, so the point would be 0, 1, so the cosine value would be 0. 180 degrees is 2 90s, so we can think of that as 2 pi over 2s, or just pi. And there we would have the point -1, 0. And so the cosine value would be -1, etc., etc. 0, and back to 1 here for cosine. Tangent is going to be very interesting here. Tangent is going to be super interesting here because it's going to be that ratio y over x. So in the case of 0 degrees, y over x is going to be 0 over 1, which is just 0. But at 90 degrees, pi over 2 is going to be 1 over 0, which we know is undefined. And so it'll also be undefined here at 3 pi over 2, and it would repeat itself at pi and 2 pi. Again, this would be 0 over -1, which is just 0, and then we're back to 0 over 1 here. 0 again. You can repeat this process for sine, secant, cosecant, and cotangent. Number 3 is asking us about the evenness or the oddness of the sine function. I promised you that this is all building toward the graph of the sine function, but it's going to be helpful to know these data points, these specific points on the graph, as well as the evenness or oddness to be able to graph the whole thing. So we want to know, is it even, odd, or neither? To be able to understand this, let's remind ourselves what even functions are. Even functions are going to be functions like x squared. And x squared, if we graph that one, come on. We can remind ourselves, have this shape, a very special relationship in which any function or any point that we have, like 2, 4, is going to have a partner reflected across the x-axis, -2, 4. That'll be true for any point, more generally, a, b. We'll have another point, -a, b. And so using this generalization, we can say that f of a is equal to f of -a. Or more generally, reading that with x, we can say f of x is equal to f of -x. That's the rule for an even function. And so for sine, we can start thinking about that. We can start examining it. Is sine an even function? If that were the case, if it were even, then that would mean, maybe, I figured out an easier way to do that. It's going to make everyone's life easier. If sine were even, that would mean that sine of theta was equal to sine of -theta. Let's examine that. My strategy here is to use an angle theta. I'm going to make up an example angle. So let's have that example angle be acute in the first quadrant as such. Then that would mean that -theta would be in the quadrant right below it. This would be -theta. Here we can say that the sine value is y over r. And for -theta, it'll be -y over r. Since these angles are the same, and since the radii are the same, then we know that the sine values here are going to be very similar. For sine of theta, our sine value is going to be y over r, and it's going to be positive, whereas for sine of -theta, it's y over r, but negative. And so this relationship is not true for sine. These two things are not equal to each other. It is not an even function, which means that maybe it's an odd function. Odd functions are functions like x cubed. And they have a relationship very similar to that of x squared. We've seen them before this year. But if this is x cubed, to understand its oddness, let's choose another point. Here I'm going to choose the point 2, ugly 2. There we go. 2, 8. Similarly, we would have the point -2, -8. Or if we think more generally, for the point a, b, we'll have the point -a, -b. And so we can say that f of a is equal to f of -a, except one of them is negative, right? So we could say something like that. Negative f of a, that would become b. Negative b is equal to f of -a, which is also negative b. This relationship is the defining relationship for an odd function. And that's what we see with sine. If we come back over here, we saw that sine of theta gave us y over r positive. Sine of negative theta gave us negative y over r. So it would be fair for us to say then that sine of negative theta was the same as negative sine of theta. And that, my friends, means that sine theta is an odd function. And if you're not convinced of this quite yet, you could prove it to yourself by example. If theta is something like pi over 6 radians, we know that sine of pi over 6 radians is 1/2. And sine of negative pi over 6 is negative 1/2. And so we can see that negative sine of pi over 6 is equal to sine of negative pi over 6, which confirms the fact that sine is an odd function. That's pretty cool. I feel good about that. Look at all those colors. So you can do similar analysis for cosine. Do similar analysis for cosine and tangent. I'll start you for cosine. For cosine, to understand it, I would choose another angle. And again, I would recommend that you choose an easy angle, like something that is acute. And then I would make another example of the other angle, the other negative angle, and I would compare their cosine values. It may be the case if cosine were an even function, then that would mean that cosine of theta would be equal to cosine of negative theta. If it were odd, it would be the case that negative cosine of theta would be equal to cosine of negative theta. And if neither of those things were true, then it would be neither. I won't tell you the answer, you can figure it out. You can do the same thing with tangent. So, here we are here with sine. And we are going to eventually graph the sine function here. First things first, is sine x, f of x is sine x here. Is it an odd or an even function? Well, we just proved to ourselves that it is an odd function. And that means that it'll also have a certain kind of symmetry. And that's going to be helpful as we're graphing this function. So a quick reminder, something like x cubed had symmetry that looked like this. That is rotational symmetry. Specifically, it is 180 degrees rotational symmetry. And we saw the fact that for any point a comma b, we would also have the point negative a comma negative b. And so these are the two things that I want to keep in mind as I'm graphing the sine function. This should be true for sine as well. So let's start out by plotting some data points. Now let's do the sine curve in a beautiful purple, shall we? So we know a couple of these things already. We know that the sine of 0 degrees, so here I'm doing this first row right here. We know the sine of 0 degrees was the y value for 0 degrees, and that was 0. So I'll plot that in right there. And the same was true for pi over 2. Pi over 2, let's see, is going to be halfway between 0 and pi. So that'll be right there. Oh no, I'm sorry, that's wrong. The y value for pi over 2 was 1. So I'm going to drop in a pi over 2, I'm going to drop in a value of 1. And then we went back to 0 at pi. and then at 3 pi over 2 it went down to -1, and then at 2 pi it went back to 0. This is the problem that we did on the first sheet. Pi over 4 is a little bit more difficult, and maybe you'll want a little reminder for pi over 4, but the sine, let's make that a little smaller, the sine of an angle of pi over 4 is going to be, well, this could be 1, 1, and root 2, so that would tell us that the sine value is 1 over root 2, which is approximately 0.707. So with that in mind, we can know that for pi over 4, just going to fall halfway between these two, so we're going to have 0.707, so that's going to be 0.6, 0.707, something like that. Now, the same thing should be true for 3 pi over 4, because these angles are both in the first and the second quadrants, with the same reference angle. Pi over 4 and 3 pi over 4 are going to fall in the same quadrants, the same reference angles. They're going to look like this, and so their sine values are going to be identical. So I can drop in that value for pi over 4, the same height. All right, 5 pi over 4 and 7 pi over 4 will have a similar relationship and a similar value, except since they're in the third and fourth quadrants, they'll be negative. So we can know that f of 5 pi over 4 will be equal to f of 7 pi over 4, and both of those will be approximately negative 0.707. So we can drop those in as well. Let's see. So here is going to be about that value for pi over 4, or 5 pi over 4 rather. So that'll be down to 0.707. Same is true for 7 pi over 4. You can already see a shape beginning to emerge, which is pretty cool. Now, we're going to have a more complicated and yet still a similarly repetitious relationship here in D. For something like pi over 6, we're going to be using a 30, 60, 90 triangle. That 30, 60, 90 triangle, this is pi over 6. My shorter side, 1/2 will be over here, root 3 over 2 will be down here, and 1 will be right there. And so my sine value is going to be that 1/2. But for something like pi over 3, so here that pi over 6 is going to give us 1/2. Pi over 3 is going to have a congruent triangle, but the y will be the x and the x will be the y, and so this one will have a sine value of root 3 over 2. And then following the symmetry that we saw earlier, then we know that those values will reflect about the y-axis. So this one will also be root 3 over 2, and this one will also be 1/2. It's the same argument that we were using up here. Same exact argument. And so, with that in mind, I can start dropping in the values for pi over 6, etc. So here is pi over 6 right there. And so that's going to have a value of 1/2. Get out of here. For pi over 3, that's going to be root 3 over 2. It's going to be up here. Let's go check out root 3 over 2. I want to be sure about the value of that one. Do I have a calculator on here? Do you guys see my calculator? Okay, let's be smart. There we go. How do I not have the calculator downloaded? Are you kidding me? This is so annoying. Oh, you're kidding me. Alright, I'm going to do it on my phone and I'll tell you what it was. Absurd. I should just have it memorized. That'd be so much better, wouldn't it be? Okay, well, here's your opportunity to go, get a drink of water. This is like your 2-minute intermission. Alright, I'm doing square root of 3 over 2. Root 3 over 2. Alright, it's about 0.866. Dang, I should have just gone with my gut. That's what I thought it was earlier. Oh well. Alright, approximately 0.866. So, 0.866 for pi over 3, which is pretty close to what we drew in anyways. And then the same will be true for 2 pi over 3. Again, about 0.866. Something like 4 pi over 3 is going to be negative 0.866. The same will be true for 5 pi over 3, negative 0.866. A little too big. There we go. And then for 7 pi over, or rather for 11 pi over 6, which is over here. Come on. Okay, got it. Shut up. We'll be back at negative 1/2. The same will be true for 7 pi over 6, etc., etc. And look at that. That, my friends, is a sine curve. And if we're going to flesh out the rest of the sine curve, we're going to see a form emerge that looks something like this. And it will continue for an infinite period of time. It goes on forever. It is said to be a periodic function. It's said to be periodic because it repeats itself. It has a period. Which is the length of one unique part. It is, you can think of this as how long it goes. The function goes until it repeats itself. And so if you're looking at the sine curve, you might be wondering, like, well, how long does it go until it starts repeating itself? The answer would be that it would cover this length. That would be one period, because everything after that is the beginning of a repetition. And so we could say that its period is 2 pi. That is the period of the sine curve. You look like you plotted several points on the graph of f of x equals sine x. This should give you some sense of what the graph looks like. But first, let's answer this question. What is the domain of f of x? Well, the domain is whatever we could plug in as an angle. And there's no angle that we can't plug in. And so the domain is all real numbers. It's all real numbers. Or in interval notation, you can write that as negative infinity to infinity. What does the graph of f of x look like as x approaches infinity? Interesting. It's a bit of a trick question, right? Because it just keeps repeating itself. It doesn't tend toward anything. As x approaches infinity, it just repeats. It repeats itself every 2 pi. Here we go. This is what we were talking about earlier. The graph of sine of x is said to be periodic in the space below. Describe what it means for a graph to be periodic. Then graph another graph, sketch another graph of f of x in the space below showing more than one period. So we just talked about it. So I'll just show you a graph showing more than one period. So we would have something like this. Here's a nice long graph in which we can show more than one period. And our sine curve would look something like this. Over and over and over and over and over again. Now I've done a few very specific things here. First, I had that intersection at the origin here. Oh, brutal. Haha, just kidding, it's still there. Because that is where the sine function begins. At a value of the angle being 0, we have that point 0, 0. And also, we should take note of how high the function goes. There is a limit on its range. It only goes up to a certain value and down to a certain value, and those values are -1 and 1. And so if we were describing the range of the function, what is the range of sine of x? Well, you'd be right to say that it's -1 to 1. Cosine x, I leave up to you. It's a very similar process to what we did with sine of x. And the more you do it, the better you'll get at it. Tan of x is complicated, but it's also so flippin' cool. And the easiest way to understand it is to start out by writing tan of x in terms of sine and cosine. We know that the tangent of an angle is its opposite over its adjacent, so it's equal to its sine over its cosine. And it's going to help us see what its domain is. Tan of x will be defined for any angle except when cosine of x, when that denominator is equal to 0. And so you can describe that as, one way to notate that is that it's all the real numbers except that set of x that make cosine x equal to 0. And so we can make a list of some of those numbers. We can describe this as all of the real numbers except for numbers like, well, what's something that makes cosine x equal to 0? Pi over 2 makes it equal to 0. 3 pi over 2, that's where x value would be 0, and so on and so on. 5 pi over 2, because it just said 0 there. 7 pi over 2. We should also remember to include negative pi over 2 and negative 3 pi over 2, etc., on and on and on and on and on. If you want to get really fancy, you could use k notation and say, except for pi over 2k, where k is an integer. Those are the values that make tangent undefined. What happens to the value of k of x? Again, k of x is tangent of x. As x approaches pi over 2. So that's interesting. What happens as x approaches pi over 2? Well, let's think about tangent x. Here, I'll put a line in between there. As sine of x over cosine of x. So as x approaches pi over 2, sine of x is approaching 1, and cosine of x is approaching 0. And so we're going to have something that's really, really, really close to 1 divided by a tiny positive number, right? So we have 1 divided by a tiny positive number, and we know that that approaches positive infinity. And so as x approaches pi over 2, it would be reasonable to say that k is approaching positive infinity. By the same logic, we can say that as x is approaching negative pi over 2, we know that sine of x is approaching negative 1. And cosine of x is approaching, what is it approaching? Well, negative pi over 2 is down here. And so cosine of x is still approaching 0 from the positive side. So now we have something that is approximately negative 1 divided by a tiny positive number. So this time we'll be approaching negative infinity. That's pretty cool, huh? So what is the range of k of x? Well, we just decided that in these two cases, we approach positive and negative infinity. And so it seems that that k goes between negative infinity and positive infinity. And so that would mean that the range was all real numbers, or negative infinity to infinity. If you're not sure about that, stick with me as we graph it, because once we graph it, I think it'll make more sense. This graph has asymptotes. Explain why and then draw them in. Well, it must have asymptotes because we have a rational function here. Ooh, it's been a while since we talked about rational functions, but we have a whole set of values. Here they are, that would make the denominator here equal to 0, which means that we would have vertical asymptotes. And so we would expect to have a vertical asymptote at pi over 2. Pi over 2 is going to be halfway between 0 and pi, so that's going to be right here. So we'd expect to have one there. We would expect to have one at 3 pi over 2, which will be right here. And then again at 5 pi over 2, which would be here. We'd expect to have one at negative pi over 2 there. And so I'm going to drop in those vertical asymptotes. We would have one right here, one right here, one right here, and another one over here. Cool. Plot k0, k pi, and k of 2 pi. Well, so that asks us, let's do this one in how about a nice blue, eh? So k of 0 will be the tangent of 0, and that one is sine 0 over cosine 0, y over x, which we saw earlier was 0. So I'll drop in that point 0, 0. And the same is true for pi and for 2 pi. The same is also true for negative pi. So we have the zeros of this function. Now use your knowledge of how tan x behaves to sketch the rest of the graph. Use a graphing utility to check your work. So earlier we said as we approached pi over 2, we approached infinity. And as we approach negative pi over 2, we approach negative infinity. And so we can already kind of see how this is going to behave. We can have a pretty good idea. But if you're not totally confident, let's plug in some value that we know the tangent of. Something like pi over 4. Pi over 4 is an isosceles triangle where the opposite and the adjacent are equal to each other, so tangent of pi over 4 is 1. And tangent of negative pi over 4 is negative 1. That's pretty good. If you want to be even more sure, you could think about tangent of pi over 3 and pi over 6. So if we consider theta being equal to pi over 6, then we would have, no, the yellow doesn't look good. There would be theta. This side would be 1/2. This side would be 1, root 3 over 2. So tangent of pi over 6, there we go, it's going to be equal to opposite over adjacent, so 1/2 over root 3 over 2, which is 1 over root 3. And using the calculator on my phone this time, 1 over root 3 is going to be, let's find out, square root of 3, 1 over that. That is going to be about 0.577. That's going to be the tan of pi over 6. So dropping that one in, pi over 6 is right here. So that is going to be a little bit higher than 0.5. And then tan of negative pi over 6, as you would suspect, would be the negative version of that. Wow, it looks like tan might be an odd function. That's pretty cool. And so putting these all together, we see a tan curve starting to emerge. And it looks something like this. And then it repeats itself. One way to think about this repetition and to make a bit more sense of it is to think about the period. Looking at this graph, we can figure out the period by figuring out how long it takes for the graph to repeat itself. And the graph repeats itself after like one of these chunks. And the distance in the x values for one of these chunks is pi, which means that the period of tan x is pi. Now that actually makes a lot of sense. And if you put that in conversation with the period of sine of x, we can see that sine of x has a period of 2 pi, tan of x has a period of pi. And that makes a ton of sense if we think about where tan is equal to itself. There are two angles on the coordinate plane, on the unit circle, where tangent has the same value. If we had one angle here, theta, this angle, theta, would have the same tangent as this angle. We'll call that theta 1, theta 2. These two have the same tangent. We've seen this pattern before. And what's cool is that we can see that tangent of theta is equal to tangent of theta plus pi. And this pi explains the period of tangent. Every pi, a tangent function has the same value. It repeats itself every pi. Sine doesn't have the same case though. For sine, we saw that for some angle theta, we'd have the same sine value for this angle. These reference angles would be the same size, but that angle theta 2, so here we could say that sine of theta 1 is equal to sine of theta 2. What's really cool about this is that if I just say that sine theta 1 is equal to the sine of pi minus theta 1. That's what theta 2 is. It's 180 degrees minus theta 1, pi minus theta 1. And so it doesn't repeat itself every pi like tan did. To get back to a period, to get to a point where it's going to repeat itself again, you have to go all the way around the circle. which is why its period is 2 pi. So there's your tangent graph. Not too much left to do on this packet. I'll walk through a few of these problems in 7, and I'll walk through it as well, and then that'll be that. So 7 asking us to find the domain and range of each of the following. So domain is going to be the easiest one. For example, for here we have 2 times sine x. So you can interpret this one as 2 times sine of x, where x you can think of as the angle. So we already know that the domain of sine of x is all real numbers, and 2 doesn't change that. So our domain is still going to be all real numbers, negative infinity to positive infinity. Here, the range changes a little bit, but not all that much, because we can think of this this transformation as a vertical stretch by a factor of 2. Or if you like to think about it algebraically, this is going to be the function 2 times, well, something on the range from negative 1 to 1. And so our range should be negative 2 to 2. If you want to think about it graphically, you absolutely can. Here, we would expect our graph to be essentially the same as the graph of sine. Oh, I'm sorry, that's so bad. I'll give you one more. There we go. Except instead of going from negative 1 to 1, this one would go from negative 2 to 2. All right, let me choose another good one for you. So I'll walk through D and F as well. So here we're finding the domain and range again, negative 5 cosine of x minus pi over 6 plus 4. So again, domain is fairly straightforward. Any angle can go into the cosine function and make it defined. And so the negative 5 and the 4 won't change that. I can still plug in any value for x. So our domain is still negative infinity to infinity. The range, a little bit more difficult, but using the algebraic technique that we used last time, I can think of this as negative 5, bad color, Blick, negative 5 times something on the range from negative 1 to 1 plus 4. And so that means that this will be something on the range negative 5 to 5 plus 4. And so our range will be negative 1 to 9. Negative 1 to 9 as our range. Some people also find it helpful to think of this negative 5 as the amplitude of the cosine curve, its height. It goes up from negative 5 to 5, and then this 4 as a shift upwards, which is why the negative 5 becomes negative 1, and the positive 5 becomes 9. Here, 2 times the tangent of x minus pi over 6. So tangent's the reverse case, right? Because with the tangent curve, we had originally, so here I'll just write this for tan of x, we had a domain of all of the real numbers except for something like pi over 2, 3 pi over 2, 5 pi over 2, etc. And so in this case, and also for tangent, we said that its range was negative infinity to infinity. And so for 2 times tangent of x minus 6, here our domain, so 2 tangent of x minus pi over 6, so here our domain, well, before it was all real numbers except for these guys that made cosine equal to 0. And so it makes sense that we'll still have a big set of numbers that make the tangent curve work. But now, earlier it was the number pi over 2 that would make cosine equal to 0. But now we wonder, in what case will x minus pi over 6 be equal to pi over 2? When would this be the case? Because this quantity right here, if that were equal to pi over 2, then it would make it undefined. And so that means that tan will be undefined when x is equal to pi over 2 plus pi over 6, which is the same as 3 pi over 6 plus pi over 6, which is 4 pi over 6, which simplifies to 2 pi over 3. So that's our first example of something that doesn't make it work. And since the period is still pi, since the period of this curve is pi, then we know that the angle halfway around the unit circle would also make it undefined. So if we add pi to this, or 3 pi over 3, we'll get 5 pi over 3. And then again, we'll make that 8 pi over 3, and on and on and on. It's a little messy, I apologize it. But that is going to be our domain. That would be the set of all the numbers that make this curve undefined. Our range before was negative infinity to infinity, and multiplying that by 2 doesn't really make a big difference. And so the range will still be negative infinity to infinity. All right, number 8. The graph of f of x is equal to cosine x turns out to be a horizontal shift of the graph of sine of x. Rewrite f of x in the form f of x is equal to sine x plus what? So, an identity can help us with this one. But before I show you the identity, let's just sketch out those two curves next to each other. So here is going to be cosine of x, and here is going to be sine of x. Let's try that one more time. Here we go. So there's going to be our graph of cosine x. Here will be our graph of sine of x. And the one big difference between these two curves is that sine of x, we can remember, starts out at 0, 0, and then rises, and then falls, and then rises again. And it intersected the x-axis at pi, 2 pi, negative pi, 0, etc. And it had its peaks at pi over 2, and its values 3 pi over 2. This would be the point pi over 2, comma 1. This would be the point 3 pi over 2, comma negative 1, 2 pi, comma 0, pi, comma 0, 0, comma 0, pi, comma 0. What would this one be? Yep, negative pi over 2, comma negative 1, negative 3 pi over 2, comma positive 1. All right, so there's sine. Cosine, though, we saw started at 0, 1. And then from there, it resembles the sine curve, but shifted. So what were these points where we had zeros? Well, this was pi over 2. This was 3 pi over 2. So this would be 3 pi over 2, comma 0, 3 pi over 2, comma 0. Here would be pi, comma negative 1. So comparing these two, we can see that going, too big blick, okay, smaller, yeah, nice. So this section, from like top to bottom to top, we can see over here, top to bottom to top. And so there is a shift. We can see this as, we can see these two functions as offset by this distance, which is a distance of pi over 2. And so, if we wanted to write the cosine curve as the sine curve shifted over, we could say that the cosine curve, there we go, yeah. We could say that the cosine curve is sine of x shifted to the left by pi over 2. And so it would be the sine curve, except, the point pi over 2 comma 1 would be shifted over such that instead it was 0 comma 1. So that would mean that when we plugged in 0, or that when we plugged in, when we plug in 0, we'll get a positive 1. So that means that when we plug in 0, we're going to have to add pi over 2 to get that positive 1. And so this should be sine of x plus pi over 2. Sine of x plus pi over 2 would be the answer there. You can use similar logic for number 9. All right. So that's all we got here. I hope this was helpful. As ever, you can chunk it up into little pieces. Please email me if you have questions. Reach out, because we are here for you. Your teachers adore you. Let us know how these things are going. And we will see you when school reopens, hopefully on Monday. Have a nice rest of your day.